Excuse me. In this video, we're going to take a look at the wave speed equation we saw in the last video. But I'm going to introduce to you the idea of a vibrating object producing a sound, and this is a tuning fork, which most of you have seen. If you haven't seen it, we'll be using it in class in the next couple weeks.
And strike the end of the tines with a rubber mallet. If a mallet is unavailable, strike it against something moderately soft like a bent knee or a mouse pad or the edge of a table. Once it's vibrating, touch the lower part of the tines near the joint to dampen out the unwanted higher harmonics. Hold the tines near your ear or the base of a large flat surface such as a tabletop or a whiteboard. Try dipping the tuning fork in water.
So you see how a tuning fork, you can see it vibrating in that video, and you can hear the sound it produces. And so different size tuning forks produce different sounds, and that brings us to the problem, as this is a PP video, so we'll do a couple practice problems. But we've got a piano string tuned to middle C, which means it vibrates so that the string or the tuning fork would vibrate back and forth 262 times a second. It says, assuming the speed of sound in air is 343 meters per second, find the wavelength of the sound waves produced by this string. So here is our equation. So for sound in air, the speed is 343 meters per second. So I'm going to write my knowns. And I know that V for this wave, my known is that V is 343 meters per second, and I know the frequency of this wave is 262 shakes per second, or cycles per second. So imagine Taylor Swift doing that. Shake, 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 262 times in a second. That would be very hard. We're trying to find the wavelength, right? So we're trying to find lambda, which looks like a backwards Y, or an upside down backwards Y. One thing to tell you that I didn't mention on the last video that is important is that the speed of a wave is independent of the frequency and wavelength, right? This speed is determined, and wave speed is always determined by the medium the wave is in. So waves travel a certain speed in water, a certain speed in air, a certain speed in metals, and so on. So this is just something to know. So to find the wavelength, we're simply going to use our equation. So V equals frequency times lambda. So lambda is going to be equal in this problem to 1.31 meters. Now, I want to talk about the human head for a second. So, human head, the ears are here, right? So then we have the eyes, right? So, human head, very angry man, I don't know. He must not have had physics, so he's not having fun. But anyway, so the human head is designed so that the ears are a certain distance apart so that when a sound wave approaches, it would hit, say, that ear first and then that ear, and we would be able to know that the sound is coming from this direction because of the time difference to get to this ear to this ear. And so we've evolved to understand the speed of sound in air, which is why when you're underwater and you hear a sound, your brain can't distinguish which direction the sound is coming from. And that's because waves travel much, much faster underwater, and so that the waves hit your ears at a much closer time. There's not as much of a time gap, and our brain has not been evolved to understand that slight difference in time. We're evolved in air where there's a much greater difference in time because waves are slower in air, and therefore that's why underwater it sounds like and it sounds like it's in all directions, and it's just really frustrating so much that you get angry because you can't figure out where Marco or Polo is. But that's why. And again, both the problem 1 and this problem can be found on page 387 in your book. So let's take a look at 2A. So let's do this 2A here. So it says the speed of all electromagnetic waves in empty space. So remember, these are not mechanical waves. They do not need a medium. And think about the sun. How does sunlight get to Earth? It travels through space. Well, what's in space? Well, nothing. So it's lucky for us that light and electromagnetic waves don't need a medium. Otherwise, we would never have existed. So the speed of an electromagnetic wave is 3 times 10 to the 8th meters per second. Just to put this in perspective, this is how fast, if you could travel this fast, you could go around the equator of the Earth 7 times in 1 second. So that's very, very fast. So it says calculate the wavelength of all electromagnetic waves emitted at the following frequencies. So for radio waves, so for A, I know that the wave velocity is equal to frequency times lambda. So then I know that 3 times 10 to the 8th meters per second equals. Now my frequency, I want to be careful here. This is 88 capital MHz. So you have to remember, and you have to go back to our Unit 1 videos when we did conversions, but this is mega, capital M, and it means 10 to the 6th, or a million of something, right? So that's why mega millions, you know, a mega is a million, right? It's 10 to the 6th. So a megahertz is 88 times 10 to the 6th hertz, and that's times lambda. So I solve A for lambda, and I get an answer of 3 point, whoops, and yes, that is the actual wavelength of a radio wave, which is maybe the height from the floor to the ceiling. So these are very, very big waves. But if you go ahead and calculate the wavelength of an X-ray, you're going to see that this one has an answer of 1 times 10 to the negative 10th meters. So much, much, much smaller. Which is why if we look on the electromagnetic spectrum, radio waves, their wavelength is in this range, 10 to 100 meters. That's radio waves. And then X-rays are all the way down here, where their wavelength is 10 to the 11th or 10 to the 12th. And of course, one thing you notice, as the wavelength gets longer, as we go this way, what happens to the frequency? The frequency gets smaller, right? So as wavelength increases, frequency gets smaller, and we can see that here. So we say that wavelength is inversely proportional to frequency. Whoop.